Hello, this is Austin Wessels, uh, and this is my final project for analytical dynamics. I chose to model the triple pendulum system and simulate the triple pendulum system, and we'll be discussing a little bit about the chaos of this system as well. So first today we're going to talk about the problem description, then we're going to go over the equations of motion, and then the simulation results, and then we'll wrap it up. Problem description. So here we have a diagram of our triple pendulum system. This system has 3 degrees of freedom, theta 1, theta 2, and theta 3. And each nth pendulum, 1, 2, and 3, will have length L sub n and a mass m sub n that's uniformly distributed across the length of the rod. Each pendulum arm is connected via mass or frictionless connectors, so we do have somewhat of an ideal system here. And those constrain that XY motion, the motion in the XY plane, to strictly about its theta direction. So you can see here we also have these R1, R2, and R3 vectors, and these vectors point to the center of mass of each pendulum, which will be useful for deriving the equations of motion. So, the r vector here. This r sub n we can easily define for all the pendulums in a general way by taking the position of the previous pendulum and looking at half the length of the pendulum and its orientation, and then half the length of the nth pendulum and its orientation, and that way we can get the position of the center of mass of the nth pendulum. So in order to do this, we also have to make this distinction where r sub 0 is 0 and L sub 0 is 0 for the first pendulum. So with this r vector defined this way, we have a simple equation for the potential energy where we have the sum from n equals 1 to 3 of m sub n, the mass of the pendulum, the gravitational constant g, and the vertical component of that position vector that we get with this dot product here. Okay, so the kinetic energy of this system is easily calculated by taking the derivative of that r vector we saw on the previous page. So we get this extra theta dot theta dot term out in the front of each of these. And then we also make this distinction that r0 dot and theta 0 dot are 0, as well as our previous distinctions or assumptions earlier. So the linear kinetic energy is the sum of n equals 1 to 3 of 1/2 m sub n times the vector r sub n squared. And the rotational kinetic energy will define our moment of inertia here. I sub n is equal to 1/12 m sub n L sub n squared. And so this is the rotation, the moment of inertia about the center of mass of our pendulum rods. And so we can calculate the kinetic energy by taking the sum from n equals 1 to 3 of 1/2 I sub n times theta dot sub n squared. Okay, so the Lagrangian will define L as the sum of the kinetic energy minus the potential energy. And so we have partial L partial Qi minus the time derivative of partial L partial Q dot I, where Qi is theta 1, theta 2, and theta 3, and Q dot I is theta dot 1, theta dot 2, theta dot 3. So the equations of motion. you'll see we're using some intermediate variables here for each equation. And even doing this, we still want to make an assumption to abbreviate these equations. For this particular simulation, we have all the lengths of the pendulum the same, L, and we have all the masses the same at M. So the equations were derived using separate lengths L1, L2, and L3, separate masses M1, M2, and M3, but for the sake of this presentation, we're going to abbreviate the equations and simplify them with the same mass for each pendulum and the same length for each pendulum. So now we'll go over to MATLAB and we can look at how these equations were derived. So first thing we're going to do is define all of our variables here. We got time, gravitational constant, then we have theta 1 and its time derivatives, theta dot 1, theta double dot 1, theta 2 and its time derivatives, theta 3 and its derivatives. Then we also have the masses and the lengths of the pendulums. Here we're helping MATLAB out by telling it that all these variables are real. Next, we define our R vector. So the first R vector is a little bit simpler because we don't have, it's not attached to a pendulum. Then we have the second R vector, so we see that first R vector pop in there, and the length of the first pendulum and the angle of the first pendulum is also important for this second pendulum. Then we have the third pendulum, position of the third pendulum. Here we have the derivatives of that first vector, second vector, and third vector. Here we're calculating our linear energy, our linear kinetic energy, and here we have our rotational kinetic energy. And then we add them all together and simplify to get the total kinetic energy given by this equation here. And you can see this equation is pretty long, and MATLAB chose to substitute in sigma 1 in here and here. I believe those are the only two spots. But sigma 1 is defined here as the cosine of the difference of theta 1 and theta 2. After we do the kinetic energy, we can look at the potential energy. So we just take the vertical component of that R vector that we have, and the mass and the gravitational constant. So yeah, you can see here that each pendulum does have its own mass in this this derivation. Then you can see the equation for the potential energy here. And we define our Lagrangian, and the Lagrangian gets a little bit more complicated here. And we have sigma 1, 2, and 3 defined for this equation going across here. Now we're going to derive our Lagrangian. So we have Q1, Q2, and Q3 for theta 1, theta 2, and theta 3. And that's the derivative of L with respect to theta 1 minus the time derivative, because we have derivative with respect to t, of the derivative of L with respect to theta dot 1. And then we have the same setup for theta 2 and theta 3. So here's theta 1, and we substitute in our nice variables for theta dot and theta double dot for each 1, 2, and 3 with this line here. And so theta 1 is this equation with sigma 1 and sigma 2 being substituted in there. Q2 similarly calculated as Q1 and substituted. And Q3, you can see the equations. So now these equations have theta double dot in theta double dot 1, theta double dot 3, theta double dot 2. So we want to separate those theta double dots so we can actually simulate the system. So we do that here in this block of code. We set up a system of equations with this matrix style. So we have a matrix of coefficients, and then x. Our x vector is the vector theta double dot 1, theta double dot 2, theta double dot 3. And so we have ax plus b equals q. In this situation, q is just 0, vector of zeros. So we're defining our a vector, b vector, q, and then we get q double dot, and that's our 3 equations. So that's theta double dot 1 is this top equation, theta double dot 2 is the middle, theta double dot 3 is the bottom equation. So you can see this equation is quite large here, and there are a lot of simplifications happening. So you can see it's sigma 19, sigma 17, sigma 18. So there were a lot of abbreviations made in this equation here, which are over here. And then we make our simplification where all the masses of the pendulums are the same, m, and all the lengths of the pendulum are the same, L. So when we make that simplification, our equation gets a lot shorter, and you can see we have the 3 equations here for theta double dot 1, theta double dot 2, and theta double dot 3. We still had to substitute in some sigma 7 here, sigma 3 over here. So all those substitutions are defined down here. And then here we put those equations into something that we can use in LaTeX. So let's get back to the presentation. So with these abbreviations, we still have the numerator and the denominator of each equation broken out so that it's easier to show in this presentation format. So n theta 1, the numerator for the theta 1 equation. You can see there's many terms in here, and it is very convenient to have MATLAB solve this equation for you and output it in a form that we can use in Simulink. Theta 2, similarly, long equation, a lot of terms. Theta 3, more of the same. Conveniently enough, all of the denominators of these equations is the same, so we have them defined here. Okay, so simulations. We can talk briefly about the simulation here. So we have some parameters with initial conditions. Lengths and masses are defined here. And then we use this runner file to actually run the simulation. So we can choose if we want to animate the simulation, record the data, how many pendulums do we want to simulate, and how long do we want to run the simulation. Pretty straightforward setting up all these parameters in the Simulink file and recording the data and then actually running the file. So for the first thing I want to do is look at the sensitivity of this system to the solvers, different solvers that are available. And I just chose to run 3 different simulations here, changing the solver and the time step while keeping the initial conditions constant over here. So if you look at our solver, MATLAB or Simulink chose ODE3 by default, and I just chose arbitrarily ODE4 and the same time step there, and then I looked at ODE3 with a smaller time step. So you can go ahead and click on the image or the link to view this video on YouTube. I'll pull it up on my computer here. So you can see the 3 pendulums are running, and they diverge, and they're not consistent with each other. Doesn't really matter which one is which, but the important thing to see here is that there are 3 different pendulums there doing 3 different things, even though they're all the same initial conditions running the same dynamics. It's just the solver or the time step that's different. So you can see they diverge around the 3 to 4 second mark, and all the angles are diverging, all the velocities are diverging also, and they're inconsistent. So here is the real good-looking simulation. So for this one, similar to the prompt for this project, we're going to run actually 64 pendulums, so a few more than were in that original prompt. We're going to use the ODE3 solver with a 0.02 time step. With our initial conditions, we're varying our initial conditions by 0.0001 radians for each run. So the first run will have a theta 3 of 2.0001, and our 64th run will have an initial condition of 2.0064 radians for theta 3 initial condition. Sorry about that. So here we can look at the video. You can click on the image or the link. The important thing to notice for the video, the red pendulum is like the first pendulum, and then it goes in kind of rainbow color, so red, orange, yellow, green, blue, and so on. So the closer the two pendulums are in color, the closer they are in initial conditions. So if we pull up our video here, you can see it looks like there's just one pendulum right now, but real quick we'll see there are many pendulums in this simulation, and they diverge pretty quickly and it turns into a mess. So if we go back here, we can slow the video down and look at how they seemingly just explode into all these different states. Okay, and then let's look at some plots for that. You can see pendulum 1, 2, and 3. One interesting thing that I noticed here in the first pendulum is it seems to be hanging down consistently. So you can see these grid lines are at 0, 2 pi, 4 pi, negative 2 pi, negative 4 pi. So all of these lines correspond to the pendulum hanging down vertically. So for whatever reason, the first pendulum seems to stay relatively vertical, hanging down. Somewhat noticeable for pendulum 2 also, you can see some striations in there, some groupings of lines, but they're still chaotic. And then theta 3, pendulum 3 is all over the place here. So let's look at theta 3. Let's zoom in on this plot where they start to diverge. So you can see this is a span from the second 3 to second 5. So there's a 2-second span of time here, and the pendulums diverge. You know, they're very close together, and they diverge by multiple rotations, 1, 2, 3, 4, 5 rotations here, separating these pendulums in the span of almost a second. And the velocities are very chaotic. It's hard to make sense of any of these plots. So with that, you can email me with any questions down here, and there'll be a link to this presentation that you just watched right here in the uploaded PDF file. Thank you.